boundary layer. What exactly mean by boundary layer? Consider a small example here. Let us consider flow of real fluid. So this all I am talking about to you about real fluid or practical fluid, as you know, which has viscosity, surface tension, all the properties. If you consider all the properties, it is real fluid. So real fluid word we have started from the fundamental chapter. So let us consider the flow of real fluid here. So this is a flow of real fluid. So now the water is flowing here, and this is a solid body. So this is a solid body which is placed in the direction when the water is moving, and this solid body, let us say it is stationary. The solid body is stationary, it is not moving. So consider a stationary solid body in the direction of the movement of water. Then what are the observations? So I am coming to the boundary layer basics. So for example, you take a solid body here, which is stationary solid body, which is not moving. So the velocity of the solid body is 0. Now there is a flow of fluid for which the velocity is u. Then what happens? So the first observation on account of viscosity, because it is real fluid, on account of viscosity, it adheres to the plates here. It adheres to the plates here. So, 1 minute. So sorry for the small interruption. And here, so we have a solid body here which is stationary, it is not moving, and this is a flow of real fluid here. Now it is moving on the stationary solid body. Then what are the observations? So the fluid is real fluid. So when the real fluid flows past a solid body, on account of viscosity, it adheres. If you remember the discussion which I informed to you in the initial classes. So here this is the fluid on the solid body, and the fluid adheres here. So because whatever the fluid which is moving here, which adheres to this plate here. So then what is the velocity of the fluid here? Velocity of the fluid on the solid body is 0. So that is, I told you, that is no slip condition, whether it is a normal flat plate, normal parallel plates or solid body, whatever it is. When there is no relative motion between a solid body and the fluid on the solid body, that condition I mentioned you, it is a no slip condition, normally asking in the objective questions of GATE. So the second aspect is, suppose the solid body is also moving, then what happens? So no doubt the fluid is flowing, and now the solid body is not stationary, now it is moving. So the body is moving, then what happens? Once again, in this case also, the fluid adheres to the moving solid body, and it is moving. So the fluid adheres to the solid body also, it moves with the same velocity as that of solid body. Important point here. Earlier case, the solid body is stationary, and the fluid adheres to it on account of viscosity, it will have the same velocity as that of the solid body, which is called no slip condition. Now, it is solid body is moving. Solid body is moving here. The fluid on account of viscosity, whether the solid body is stationary or moving, it adheres to the solid body. So the fluid on the solid body is also moving with the same velocity as that of velocity of the solid body. So those two are different cases here. Now we about moving solid body can consider only stationary solid body. Consider only stationary solid body. So here the velocity here is 0, and suppose if you consider slightly away from the solid body, so no doubt the velocity here is 0, and you can assume a nonlinear variation for the flow in the region away from the solid body. Suppose if you go slightly away from the solid body, what happens here? So you can expect that the fluid is moving, but not with full velocity, with reduced velocity on account of viscosity, on account of the solid body. And suppose it slightly go away, and at particular point, the velocity of the fluid slightly away from the solid body, it reaches the free stream velocity. Then this is free stream velocity here, then this is 0 here. So then what is boundary layer? So boundary layer is a layer in which the velocity of the flow changes from 0 here to the free stream velocity. So this is the boundary layer. This dotted lines here we have shown, this is the boundary layer. So here this is velocity 0 here, and the this velocity capital U is the velocity of the real fluid. So slightly away from the solid body, the fluid moves with the velocity capital U. So from here to here, and this entire area is a boundary layer. So this is the boundary layer, and the theory related with boundary layer is called boundary layer theory. I am repeating, boundary layer is a layer in which the flow changes from, fluid velocity changes from 0 to capital U, and this is the area. This area is called boundary layer, and the theory related to boundary layer is boundary layer theory. Okay, the other way, and we have take two regions here. One is the fluid inside the boundary layer, and the other one is fluid outside the boundary layer. So take two regions here. One is the flow of fluid in the boundary layer, in this area, and the flow of fluid outside the boundary layer. Then what happens here? So here if you take shear stress, what is the equation of shear stress? The fundamentals of fluid mechanics, they will come for each and every chapter. It has to remove chapters in the fluid mechanics. It's the last chapter of fluid mechanics. So Newton's equation of viscosity, as you know, shear stress is equal to mu to d by dy. If you remember, this shear stress is mu, dynamic viscosity, into d by dy. Tau is equal to mu to d by dy, dynamic viscosity. So consider the fluid inside the boundary layer here and fluid outside the boundary layer. And suppose if you find out the change of velocity with reference to direction. Tau is equal to mu to d by dy. So what is du by dy for the fluid inside the boundary layer? So for the fluid inside the boundary layer, so du means change of velocity. So here the velocity is capital U, and here the velocity is 0. Here the velocity is capital U, and here the velocity is 0. So the change of velocity is equal to capital U minus 0. So then the change of velocity is capital U minus 0, and the distance here is y from here to here, let us say, and dy is distance from the two points under consideration. Here on the boundary the velocity is u and here 0. This is the vertical distance here, that is dy. So this is called velocity gradient. So within a small distance there is a maximum change in velocity. Then what is du by dy? Gradient is maximum. In other words, I can say that for the fluid inside the boundary layer, as du is equal to u minus 0, du by dy. So du by dy is maximum. So when du by dy is maximum, what happens to shear stress? So shear stress is equal to tau is equal to mu to du by dy. So as du by dy is maximum, the shear stress is also maximum. Sir, for the fluid inside the boundary layer, you can say that the velocity gradient is maximum. In view of maximum velocity gradient, the shear stress is also maximum. That is the observation for the fluid inside the boundary layer. Then go to the fluid outside the boundary layer. Fluid outside the boundary layer. If you see the velocity distribution here, so fluid on the boundary layer having velocity capital U, and if you are going away, so there is no influence of solid body here. So the velocity remains constant. The velocity of the real fluid is same. There is no influence of boundary layer here. So the velocity is same. Then what is the change of velocity here? So change of velocity here is u. I mean du by dy. What is the velocity gradient? So du by dy. So du by dy is du change of velocity. Here also u and here also u. So that means the change of velocity is equal to 0. So the velocity gradient is 0. When the velocity gradient is 0, what happens to shear stress? So the shear stress is tau is equal to mu to d by dy. The velocity gradient is 0. So shear stress is also equal to 0. Shear stress is also equal to 0. Then, so when shear stress is equal to 0, shear stress is 0, then means there is no resistance for the fluid outside the boundary layer. So for the fluid inside the boundary layer, we have a resistance because of the maximum velocity gradient, because of the maximum shear stress. That is the concept here. Then consider the boundary layer along a flat thin plate. Consider a boundary layer along a flat thin plate. Another growth of boundary layer. So this is the case here. Then how will you consider the flow over a plate? So this is leading edge here. This is the leading edge here. A is the leading edge. And consider the flow of fluid here, flow of real fluid. So this is the flow of real fluid here, flow of real fluid. So consider the flow over the flat plate. So this is also stationary. Boundary layer along a thin plate and its characteristics. So this is a plate here. This is stationary. It's a thin flat plate. This is stationary here. And now the fluid is flowing. So fluid is a real velocity. Now it is flowing. What happens here? So this is called leading edge. This is called leading edge. The point at which the boundary is starting here. And again, as it is stationary, when the fluid is flowing over a solid body, on account of viscosity, what happens here? It adheres. The fluid on the solid body or on the flat plate will have same velocity as that of solid body. So the bond layer starts from here. So then it is increasing. The bond layer is increasing. It is not decreasing here. What is the reason? So the reason here is whatever the fluid which is coming here, it will be resisted by the shear stress which is opposing the flow. So we have the shear stress here, we have because of this plate, we have the shear stress here. Just remember the previous discussion. So the velocity gradient is maximum. We have a shear stress of the fluid here on account of viscosity because of this flat plate here. So because the shear stress is opposing the movement of water in the opposite direction, whereas the fluid is moving in the forward direction, so the boundary thickness increases here. So the boundary thickness gradually increases here. So this is the so for example, then we have the different types here: laminar boundary layer, transition zone, and turbulent boundary layer. Laminar boundary layer, turbulent boundary layer, and also laminar sublayer. So a clarity must be required for you. What exactly mean by laminar boundary layer? What exactly mean by turbulent boundary layer, and laminar sublayer, etc. So here, if you see here, then how will you find out this is a laminar zone or turbulent zone? Laminar zone and turbulent zone. So here, from A to B, let us say want to find out Reynolds number. So how will you know whether the flow is laminar or turbulent? For the pipe flow, that is for the pipe flow. So for the pipe flow, Reynolds number is less than 2000 for the laminar flow. Reynolds number less than 2000 laminar flow. So Reynolds number more than 4000 is turbulent flow. So the Reynolds number which is equal to less than 2000 for laminar flow and more than 4000 for turbulent flow, that is for circular pipe. So for the flat plate, the value of Reynolds number which is equal to 5 into 10 power 5. You should remember. So you should not take less than 2000 for this case. So for the flat plate, long flat plate, in this case, particularly considering the laminar boundary layer, etc., you can expect a laminar flow in the boundary layer area when the Reynolds number is less than 5 to 10 power 5. So earlier it is less than 2000 for circle when the fluid is through a circular tube. Then Reynolds number is less than 2000 for laminar flow. Whereas here, try to remember, that's why I am stressing, Reynolds number equal to 5 into 10 power 5 or less than 5 to 10 power 5 for the laminar flow. So now, the laminar flow equation, we can take distance V to X by kinetic viscosity, Vd by nu, the same equation. But in place of diameter, this is X here, the value here is X here. So the X is the distance up to which laminar flow is existing. That means this is the area up to which laminar flow is existing. So this is X here. Then, how will you find out the value of X here? So it is required to find out this distance here, A, B distance is X here. So now we have the equation Rn is equal to 5 into 10 power 5. Rn is equal to 5 into 10 power 5. Rn is equal to 5 into 10 power 5, which is equal to Vx by nu. So the kinetic viscosity of the water is known, 10 strokes, point, that. And velocity is known here, velocity of the real fluid is known here. And you can find out the value of X here. So X is equal to 5 into 10 power 5 into kinetic viscosity by velocity. So if you know the value of X, so up to that, so this is known here, then you can say that this is laminar boundary layer. Very simple, laminar boundary layer. Then once the laminar boundary layer is over, then what happens? So here, there is a growth of boundary layer here. So because this fluid is already retarded, because of the shear stress, whatever the fluid which is in the boundary layer, it is retarded. And again, the same fluid is moving here, again it is retarded. And the same fluid is moving here, again it is retarded. So there is always a growth of boundary layer. Increase. Then there is a transition zone in which the flow is between laminar to turbulent. Laminar boundary layer means, as you know, the flow is smooth, stable, regular, and no mixing of fluid particles when it is considering the flow here. And this is turbulent, this is a transition zone wherein the flow changes from, laminar to turbulent, wherein the flow changes from laminar to turbulent. So then this is laminar zone. So once it is complete, transition zone, once it is completed, then we will go to the turbulent boundary layer. So then how can you say that it is a turbulent boundary layer? So the issue here is the fluid inside is turbulent, the fluid in this area, in the boundary layer area is turbulent. In other words, you can say that the flow is irregular, erratic, and disturbance, intermingling of fluid particles from top to bottom and bottom to top, irregular, erratic, all these things, then you can say it is a turbulent flow, and the layer is a turbulent boundary layer, wherein the boundary layer have maximum thickness here, so that is turbulent boundary layer, and we have FG portion is turbulent boundary layer. We have a small portion here, it is called laminar sublayer. Normally in the object type question, he is also asking what is a laminar sublayer. So laminar sublayer is a layer in which, so this is a, see here, this is a turbulent zone. So this is a turbulent boundary layer. Even in the turbulent boundary layer, there is a small layer very close to the solid plate. A laminar sublayer is existing. And what is meant by laminar sublayer? Laminar sublayer is a layer which is formed normally adjacent to the flat plate and is a turbulent boundary layer zone. Otherwise, it is laminar boundary layer, not laminar sublayer here. So laminar sublayer is a layer which is very close to the solid body and formed in the turbulent boundary layer, and the flow is laminar. A slight portion, a slight thickness, if you see here dotted lines here, wherein the flow is laminar, even though the total layer is turbulent, even though it is a turbulent zone, so that's why it is called laminar sublayer. Laminar sublayer, the part of that. This you can expect that when the plate is very smooth, when the flat plate is smooth, you can expect that there is a smooth flow, regular flow. In that case, you can expect that it's a laminar sublayer. This is very important. Leading edge, laminar zone, transition zone, turbulent zone, laminar boundary layer, turbulent boundary layer, and laminar sublayer. Then boundary layer thickness. What is meant by boundary layer thickness? And what are the factors affecting boundary layer thickness? So this is the sketch here. Once again, consider plate here and flow here, flow of fluid, consider. And what exactly mean by thickness? Thickness of boundary layer. There are two important issues for getting thickness. One is the thickness should be always measured normal to the plate, exactly vertical here, normal. Thickness should be measured normal here. And the other one is thickness of the boundary layer represents in which the velocity change starts from 0 here and to the free stream velocity. So here the velocity is free stream. Velocity is free stream here. That means from here, from the position C to B, if you measure vertical distance, that is boundary layer thickness. So it has taken some point here A to B, and if you want to find out the boundary layer thickness, so boundary layer thickness is, it starts from the point here, and from the vertical distance from here to here, vertical distance from here to here, so this is delta or boundary layer thickness, and in the boundary layer thickness, strictly speaking, it is defined as the boundary layer thickness is thickness which is measured normal to the plate, in which the velocity changes from 0 here, 0 to 99% of free stream velocity. Exact definition, mathematical definition. The velocity change here is 0, at B is 0, velocity change here is the velocity of real fluid, and this is thickness here, BC is the thickness of boundary layer. Then we have different approaches here, displacement thickness, momentum thickness and energy thickness. And before that, what are the factors affecting the boundary layer thickness? Important question. Factors affecting boundary layer thickness. For example, this is the leading edge. First factor you consider. This is the leading edge. And when the distance from leading edge increases, in other words, we are going downstream to the plate. This is upstream here, let us say, we are coming down. Then when the distance from leading edge increases, then what happens here? So this is the boundary layer thickness here, and this is the boundary layer thickness here, and this is the boundary layer thickness here. So the boundary layer thickness increases with increasing distance from the leading edge. So this is the leading edge. When the distance is increasing here, the thickness is increasing. If you take thickness here, this one. If you take thickness here, this one. So the thickness increases with increasing distance from leading edge. When x is more and more, we can get more and more thickness of boundary layer. That is first factor. Then, now the Kahneman viscosity is increased. Viscosity is increased. So if the viscosity is increased, what happens with the boundary layer thickness? So let us say the mu value increases here, tau is equal to mu to dy by dy. The viscosity is more for the fluid, then what happens to the boundary layer thickness? Increases or decreases? All the factors refers to either increasing thickness or decreasing thickness. So here, the boundary layer thickness increasing or decreasing with viscosity. When viscosity is more, more and more resistance offered in the opposite direction. So with increasing viscosity, the boundary layer thickness increases. So the boundary layer thickness increases with increasing viscosity. More and more viscosity, more and more adhesion, and more resistance towards the forward flow. So that we can say that the boundary layer thickness increases with increasing viscosity. Number 2. Number 3. Let us say the velocity of fluid is increasing. Earlier we have some other velocity, now the fluid velocity is increasing. Then what happens to boundary layer thickness? So when the velocity layer is increased, then what happens to boundary layer? So the boundary layer thickness, more and more velocity, that means we are having more forward force compared to backward force. Backward force is due to viscosity. Now we are applying more force here, we are giving more velocity here. When the velocity is more in the forward direction, so then what happens here? So the resistance also decreases here. So that means when velocity is more, the boundary layer thickness decreases here. That is a third factor. So meanwhile, you see these equations here. There are 3 equations here: displacement thickness, momentum thickness, and energy thickness. So displacement thickness, just observe all the 3, and displacement, momentum, and energy thickness. And this is the problem. Just see this problem.
Also, contact touch
So the problem, find the displacement thickness for the velocity distribution in the boundary layer given by small u by u is equal to y by delta. When u is the velocity at a distance y from the plate and u is equal to capital U and at y is equal to delta, where boundary layer thickness. Delta is the boundary layer thickness. Very simple problem. He has given the velocity distribution. What is small u? Small u is the velocity of the fluid. Suppose if you take the figure, small u is the velocity somewhere here. Velocity of the fluid at a distance y. Small u is the velocity of the fluid at a distance y. So when the delta layer boundary layer thickness means from here to here. So when y is equal to delta, that means from here to here, the velocity is capital U. That's what. So he has given the small u is the velocity of the fluid inside the boundary layer. This is the velocity of the real fluid, which is equal to y by delta. So where u is the velocity at distance y from the plate, and u is equal to u at y is equal to delta, where delta is boundary layer thickness. Then how will you find out displacement thickness? So we have the equations here for finding out displacement. You try to remember all the three equations here, not necessary derivations. The displacement thickness is integral 1 minus u by u dy, and momentum thickness integral u by u 1 minus u by u dy, and energy thickness integral u by u into 1 minus u square by u square dy. Try to remember all the three equations. So when the displacement thickness equation is 1 minus u by u into dy, and substitute the value y by delta, so 1 minus y by delta into dy, then do integration. So y by delta 1 minus 1 place y, and u by u is y by delta, so delta is a constant, so then y square by 2 delta, and he has given that y is equal to delta here, y is equal to delta, substitute the y is equal to delta here, so delta minus delta square by 2 delta, delta minus delta by 2, the answer is delta by 2. Very simple cycle problem. If you know the equation and if you know what is what, then you can easily solve the problem. Then the other one is separation of boundary layer. Methods to control the separation. This is also another important discussion. So this I have taken from textbook, and also acknowledge the ACE material, ACE Chief Murthy garu, and also fluid mechanics and hydrodynamics from Mandal for taking their material for the sake of the students of Andhra Pradesh. I acknowledge them for their help. And here, this is a figure from the textbook. All the material from some sources here. I acknowledge all the, all the writers who have given the information, and I acknowledge them deeply. So this is a bond layer thickness here, and now there is a flow. This is the curved plate. So here, I mean to say that this is the curved plate. So when it is a curved plate here, when it is a curved plate, and consider the flow of real fluid here. So this is the pressure distribution. This is the pressure distribution. The pressure is decreases from A to C and again increases here. So the pressure gradient is more than 0 in this region. So my discussion pertains to this area. So the pressure gradient is more here. The pressure is increasing. When the pressure is increasing, the velocity is decreases. When the velocity decreases, the boundary thickness increases here. So I am discussing about this region here from C to D, the importance of separation of flow. So the pressure here from C to D, the pressure is increases here. When the pressure is increasing, what happens to velocity? Velocity decreases here. When the velocity decreases, in view of the pressure increase, the boundary thickness increases. If you see the boundary thickness here, this is the value of boundary thickness. From here, this is the value of boundary thickness here. So the boundary thickness here is more compared to this one. Again from here, the boundary thickness is more compared to this one. So the boundary thickness goes on increasing from C to D. Then, in view of pressure increase, as the boundary thickness is increasing, that means whatever the shear stress, again shear stress is more and more when you are going down. When the pressure is more, and pressure is more, positive pressure gradient is more, and boundary shear is there, and all these things, what happens here is the fluid inside the bond layer suddenly comes to rest. So somewhere here, the fluid here inside the bond layer. So this is a separation point here. The fluid here is suddenly comes to rest. We have some velocity here. We have some velocity here, but whereas somewhere here, the velocity of the fluid inside the bond layer suddenly comes to rest. So this is called separation point. Separation point is the point at which the velocity of the fluid in the bond layer suddenly comes to rest. Then you see here the bond layer thickness is more here. And still if you move across, move forward, when you move forward from separation point, what happens here? So the boundary shear is more and the pressure is more and the velocity is less here because of all these things and the same fluid, water also. So this is the forward flow and below this line there is a back flow. That's why if you see the velocity distribution, So velocity distribution is velocity increases here, and whereas this is the velocity in the opposite direction, velocity in the opposite direction. So this is the velocity in the opposite direction. So this is the velocity in the forward direction. So then what happens here? Velocity in the opposite direction, velocity in the forward direction here. And this is, suppose if you see here, this is the line which is separating forward flow and backward flow. This is called separating streamline. So this is the backward flow in the bonds to rest, and there is a reverse flow also, because the same flow is further retarded and positive pressure gradient and bond shear all acting, and also velocity is less. So there is a flow of water in the reverse direction, So when you separate the forward flow and backward flow, that line is called a separating streamline. Very, very important. Separating streamline. Important for object type questions. This is the separation of streamline, separation of boundary layer, because the bond layer supposed to be along this line, but here the bond layer is separated here because of negative velocity. And then how will you control this separation? That is another issue. Methods to control the separation. The one aspect is motion of solid body, acceleration of fluid in the boundary layer, acceleration of fluid in the boundary layer, and suction of fluid in the boundary layer. These are the three methods based on which you can control the separation of flow. Then what is by giving motion of solid body? For example, you take here, just a sketch I am taking. So this is the solid body, let us say. By giving motion, now this is moving. So this is, for example, if you take a circular shape. So this is rotating, circular shape is rotating, and what happens here? So when it is also rotating, this is also coming. So that means when it is rotating, it is giving more energy here. It is giving more energy. So when the first version is giving motion to the solid body, this is the solid body, we are giving motion, movement. So if we take a circular cylinder, let us say the circular cylinder now it is rotating, so this is moving like this. In other words, it creates additional energy, it gives additional energy for the fluid inside the bond layer. So when the energy is more and which counteracts the viscosity, then there is no chance of formation of boundary layer if you give motion to the solid body, but which requires additional energy. That is one aspect. And second aspect is acceleration of fluid in the boundary layer. So that means you have the bond layer here. Now you are accelerating the fluid inside the bond layer. So here the fluid here, this is the bond layer. Now you can give additional energy. Let us say from the interior solid body, you are giving additional supply to the water here. That means you are giving additional energy from the interior of the body. So that means you can accelerate the fluid velocity for the fluid in the boundary layer, so that you can avoid the formation of separation of boundary layer. Important. Try to understand this concept here. So you are giving more energy for the fluid inside the boundary layer by means of acceleration of fluid here. Whatever the fluid, you can give additional supply through the solid body for the water here, so that there is no chance of formation of boundary layer. Acceleration of fluid here in the boundary layer. That means you are giving additional energy. So the additional energy will be supplied through solid body here. The water will be supplied through solid body, and we have additional energy. There is a chance of elimination of boundary layer formation itself. The third one is suction of fluid from the boundary layer. So this is slow moving fluid here, you have a slow moving fluid, suction. Acceleration is you are giving more than the suction means you are taking the fluid in the bond layer back to the solid body. Suction. Suction means negative. So you can apply suction here. There is a interior of the body here. You can remove all this fluid and it can be sucked into the solid body. So when there is no fluid which is close to the solid body, then there is no chance of formation of bond layer. The separation can be avoided. So the fluid inside the bond layer can be sucked inside the solid body by means of the separation of bond layer. Methods to control the separation, motion of solid body, acceleration of fluid in the bond layer and suction of fluid in the bond layer. Now the other case is drag and lift. Drag and lift. When the fluid is flowing over a solid body, okay, take this sketch here. So consider the flow here again, flow of real fluid. The entire chapter, the flow is flow of real fluid, flow of real fluid. So contain the flow of real fluid over the stationary. So I can expect always when it is a stationary body, when it is not moving, force is exerted by fluid on the body. The force is exerted by fluid on the body. Then what happens here? Then what happens here? So you can see that the force exerted by fluid on the body is Fr, and it can be resolved into two directions here. One is the force parallel to the direction of the motion of the fluid here. The force parallel to the direction of the motion of the fluid here. And you can also resolve the force which is perpendicular to the direction of the motion of the fluid here. Force parallel to the direction of the motion of the fluid, and also force perpendicular to the direction of motion of the fluid here. So this Fd is called drag force. So drag force is the force exerted by the fluid on the bend in the direction of the motion of the fluid here. Important objective questions come at the end of this chapter of GATE. You can say that. So this is the drag force. This is the drag force which is applied in this direction. And it is, the force component is resolved in the horizontal direction. So this is the force occurred in the direction of motion of the fluid, because this is and this should be parallel. That is drag force. And take lift force here. Lift force is the normal force exerted by fluid on the surface in the direction normal to the direction of the motion of the fluid. So this is the drag force. Drag is pulling, and this is lifting. So lifting is always in the vertical direction, drag is always in the horizontal direction. So lift force is the force exerted by fluid on the bend in the direction normal to the direction of flow. In other words, the vertical component of Fr is lift force. So this is the concept of drag force and lift force. Then you take a general example. You consider the actual condition. Take one case, there is a flow of air over buildings. Flow of air over buildings. What happens? So the air is moving and in between there is a building. So obviously the air is moving and building is stationary, but there will be force by the air on the building. That is the practical example. That is the practical example. Take another one. Flow of water over bridges. So now the water is moving and we have a bridge pillars. Then what happens here? So there is a flow of water over bridges here. I am taking in a practical sense. Flow of water over bridges here. So when the water is flowing over bridges, there will be force by the water on the bridge. The bridge has to, for example, take a dam on that. So dam is a hydraulic structure constructed across the river to store water on the upstream side, and dam is obstruction for the water to flow of water, or dam is required to raise the water level on the upstream side for the purpose of irrigation and navigation. Then the surface, entire surface, you can take it as a solid surface. So there is a continuous flow of water, and as it is obstructing, so there is a force by the fluid on the dam. That is a practical example of this chapter, drag and lift. Similarly, now we take another one, aeroplane, movement of aeroplane in air. So air is moving and aeroplane is also moving. Then what happens here? So there is a force of air on the aeroplane. Similarly, take a ship which is moving in a sea, moving water. So because of that, there is once again there is a force by water on the ship. So these are all the practical examples. Then how will you find out the expression for drag and lift? So how will you find out the expression for drag and lift? So drag is the force acting in the direction of the motion of the fluid, and lift is the force acting in the direction perpendicular to the motion of the fluid here. So this is the direction of the velocity here, and this is the x-axis direction, the direction of the motion of the fluid here. And which two forces you will consider normally here? Only two forces. One is the pressure force, the other one is shear force. Pressure force always acts normal to the surface of the contact. There are two importance. One, the forces here are two forces. So that means you have considered arbitral shape, and this is required. This I am discussing for arriving drag force and lift force and resultant force. So drag force is, suppose if you consider arbitral shape and consider the flow of fluid over arbitral shape, and it is required to find out the drag force and lift force for this case. And the drag force, before that, the forces under consideration for this case, pressure force and shear force, So this is the pressure force and this is the shear force here. And the pressure force, as you know, always acts. If we take a small element here, so this pressure force always acts normal here. And this is the shear force, which is always acts tangent to the surface here. So one is tangent and one is normal here. Now how will you find out drag force and lift force here? Drag force is, so we can resolve these forces, in the direction of motion of the fluid is the drag force, and resolve these forces in the direction normal is the lift force here, simple. Then how will you find out drag force for this case? Then you take the pressure force here, and pressure force is P into dA, and shear force is tau 0 into dA. Then resolve this pressure force here. What is the angle here? When you want to resolve this in the direction of motion of the fluid, so it is P dA cos theta. So the total is 180. Here. This is 90. Between this is 90 and this is theta. This will be 90 minus theta. As the total is 180 and theta is given and this is 90. So 180 minus 90 minus theta. So this will be 90 minus theta. The angle here. So you can resolve with PDA in the direction of the motion of the fluid. So PDA in the direction of motion of the fluid is angle is cos theta. So PDA cos theta, that is the pressure drag. This is also called pressure drag. So total drag is equal to pressure drag plus friction drag. So pressure drag is the pressure force in the direction of the motion of the fluid, that is the pressure drag. So which is equal to PDA cos theta. And what is friction drag here? So friction drag is the shear stress is tau 0 dA and the angle is 90 minus theta, and resolve this in the direction of the motion here. The angle is cos 90 minus theta. So tau dA cos 90 minus theta, cos 90 minus theta is sin theta. Your trigonometry, you need to remember the trigonometry also. Mathematics, trigonometry and physics, everywhere you get in engineering. So tau 0 into dA into cos 90 minus theta and sin theta. So this is the friction drag, this is the pressure drag. So the total drag is equal to pressure drag. Pressure drag is dA cos theta, and friction drag is tau 0 dA cos 90 minus theta. Now we have a pressure drag and total drag for small element, and if you want to find out the drag force for the entire element, you take the integration. So integration of drag force and integration of pressure drag and friction drag, so that you can find out for the entire surface here. So this is drag force, and similarly lift force. So lift force is take the lift force here. Lift force, as you know, so this is, you see here, lift force. So lift force is resolve the pressure force and drag force in the direction perpendicular to the direction of the motion of the fluid here, lift force. And now we resolve the pressure force in the direction normal here. Then the sine angle here is, so FL is the pressure force acting in the direction here, and PDA sin theta. But if you see here, this is acting in the downward direction. So take positive sign in the upward direction. Take positive sign in the upward direction. So now it is PDA, and the angle is sin theta. So minus PDA sin theta. The pressure in the direction here, because it is moving down, and take next the shear in the direction of the motion of normal to the, in other words, vertical direction. So tau 0 into dA, and the angle is sin theta here, sin 90 minus theta here, which is equal to cos theta. So tau dA sin 90 minus theta is the shear force in the vertical direction. So the lift force is equal to PDA sin theta, PDA sin minus PDA sin theta, and tau dA sin 90 minus theta, do integration, and you can find out the total lift force. You can find out the total lift force for the entire surface here. So once the drag force and lift force is known, you can also find out the resultant force. So resultant force Fr is equal to square root of Fd square plus Fl square. This is the expression which is really necessary you to understand, and you can have a generalized equation also. So the drag force is friction drag plus friction drag plus friction drag, and lift force is the force due to pressure and force due to friction. Pressure lift and drag lift, pressure and friction. And you can present drag force and lift force in the more generic form. So the value of CD is the quotient of drag, and A is the cross-section area, and this rho is the mass density, and U is the velocity. You can find out the drag force. So drag force is equal to quotient of drag into cross-section area, mass density, and square of the velocity by 2. And similarly, you can also find out lift force. So CL is the quotient of lift. CL is the quotient of lift, which is equal to, lift is equal to CLA, rho is square by 2. So CL is the quotient of lift, and the remaining are same. A is the cross-section area, and rho is the mass density, and U is the velocity, and by 2. This is the drag force and lift force. Take a problem on that. Problem. A flat plate 2 meters by 2 meters moves at 40 kilometers per hour. A flat plate 2 meters by 2 meters moves at 40 kilometers per hour in stationary air of specific weight. Stationary air of specific weight kg force under 0.2 and CR is equal to 0.8. CR is equal to 0.8. Find drag force, lift force, and also resultant. So he has given convert to meters per second. So the velocity is 11.111. So 40 into 1000 kilometer into meters by hour into 60 into 60. So 40 into 1000 by 60 into 60. That is U 11.11. I mean 11.11 meters per second. Velocity and mass density is W by Z. So 1.25 by 9.81. 1.25 by 9.81, which is 0.127 ms per meter cube. So that is mass density. He has given in specific weight. Specific weight is equal to W by rho is equal to W by Z 0.127. Then you use the drag equation CDA rho square by 2. CDA rho square by 2 and lift is CLA rho square by 2. So CD quotient of drag he has given. Quotient of drag is 0.2. CD is 0.2 and area 2 into 2 4 meters. Area 2 into 4 meters and rho is 0.127 and you can substitute the value U here 11.11 square by 2, that is 6.25 kg force, and lift force is equal to CL. CL is quotient of lift is 0.8 and area is 2 into 2 and rho is the mass density of 76 kg force. Then we have objective questions and we'll have a short break for 5 minutes and we'll have objective questions and we'll complete this chapter with objective questions. It may take half an hour or 40 minutes, whatever it is. And if time permits, I will also discuss some important objective questions at the end for another 5 to 10 minutes and I will complete by stipulated time 15 to 20 definitely. And take a short break, we'll take a short break and we'll take water and again refresh and Okay, we come into the last part. Objective questions. For first question, for airflow over a flat plate, velocity u and boundary thickness, it has given some equation u by u is equal to 3y by 2 delta minus 1 by 2 y by delta whole cube, and delta is equal to 4.64 x by square root rg. If the free stream velocity is 2 meters per second, free stream velocity means capital U, and air has a kinetic viscosity of 1.5 to 10 power minus 5 meters square per second, and density of so and so 1.3 kg per meter square, then wall shear stress at x is equal to 1 meter is. So we have the data here, rho, the mass density is known here, and kinematic viscosity is equal to mass density by rho, which is he has given 1.5 to 10 power minus 5 meters square per second, and u is 2 meters per second, and x is distance up to which the flow is laminar, that is 1 meter here. So you can use Reynolds equation here. So mu by rho is kinematic viscosity, so 1.5 into 10 power, this is 10 power minus 5 this is, and this is 2 into 1. So here the velocity here, if you see here, the velocity here is 2 meters per second 2, and L is 1 here. So you can find out Reynolds number here, and the shear stress is tau naught is equal to mu to d by dy at y is equal to 0. So where u by u has given u by u is equal to 3y by 2 delta minus y cube by 2 delta cube, and you can find out d by dy. So d by dy, u is a constant value, so d by dy is 3y by 2 delta is 3 by 2 delta, and y cube by 2 delta cube, 2 delta cube is constant, y cube is 3y square. So d by dy at y is equal to 0, at y is equal to 0 means this 0, and this is 3u by 2 delta, and he has given delta is equal to 4.64 x by square root of rg, so 4.64 into x, and this Reynolds number already we have arrived here, and putting x is equal to 1, so it has given x is equal to 1, x is equal to 1, so find out delta here. So delta is equal to 4.64, again the Reynolds equation, which is equal to 0.127 here, this is the boundary thickness, and we have the equation. He has asked to find out the shear stress, he has asked to find out the shear stress mu into d by dy which is equal to, and d by dy here we have a 3u by 2 delta, 3u by 2 delta, and mu value we have given here, so this is 3 by 2, and u by delta, so capital U, so capital E is 2 here, capital is 2 here, and delta is 0.0127, and this mu you can see here, this is the kinetic viscosity 1.5, sometimes students are doing mistake here. So this mu, always you should know the fundamentals, so this mu is equal to kinematic viscosity, so multiplied by, what is this here, this is density, so mu is equal to mu by rho, and mu is equal to mu into rho, so mu is the kinematic viscosity and rho is mass density, and finally this is 4.355 into 10 power minus 3, and this is answer is C. The thickness of the laminar boundary layer at a distance x from the kneeling edge over a flat plate varies as. So the equation is delta by x which is equal to 5a square root Rn, or delta is equal to 5x or proportional to 5x by square root Rn, which is equal to rho bx by mu. You can say that it is proportional to x power 1 by 2. It is proportional to 1 by 2. So the thickness of the laminar boundary layer, which is proportional to square root of the distance here, x 1 by 2, based on this equation. The other question, flow separation is caused by. Flow separation always by positive pressure gradient. I mentioned and discussed at length while you are discussing at separation of boundary layer. separation of boundary layer. So which is a positive pressure gradient. Any separation, the main thing is a positive pressure gradient. The answer is adverse C, a positive pressure gradient. The necessary and sufficient condition which brings out separation of boundary layer is d by dx more than 0. False, because separation takes place when du by dy. So that means the velocity change at the affected point is 0. Not only more than 0, particularly d by dy when it is equal to 0. That's why it's false. So consider the laminar boundary layer or a heated flat plate. The free stream velocity u w at some distance x from the leading edge, the velocity boundary layer thickness is delta t. If the Prandtl number is greater than 1, then what happens? So Prandtl number, as per the definition, is molecular diffusion of meant by molecular diffusion of heat. From question, since the Prandtl number is more than 1, he has already given a hint here greater than 1. So the velocity, so as it is a ratio, so the velocity boundary thickness delta V is more than 1. So that's why the answer A is correct. Delta V is more than 1 here. So the second one, a fluid flowing over a flat plate has the following properties. Dynamic viscosity is 25 to 10 power minus 6. And the specific heat 2.0 joules, this J represents joules. So this is kg force meters per second square. The unit it has not given properly, but this is kg force meters per second square. Kg for second square per meter. Okay. So this is specific heat here, and thermal conductivity is 0.05. The dynamic boundary layer thickness is measured to be 0.5 mm. The thickness of thermal boundary layer would be. So we have the equation here, delta by delta theoretical, the boundary layer thickness ratio, which is equal to the P. So the equation finally, mu Cp by K. So here mu he has given 25 to 10 power minus 6. And this is thermal specific heat. Specific heat is 2000. So 2000, I mean actually 2 kilojoules here, and you can convert it into 2000 J by kg K. And that by K he has given thermal conductivity 0.05. So try to remember this equation, you can solve this problem. So this is equal to 1. So this is when it is equal to 1 and delta is equal to delta n. So that is the answer here. Answer is B. So this is the ratio of that. For a flow of fluid or a heated plate, the following fluid properties are known. Viscosity 0.01 pascals second. Pascals is Newton per meter square. Newton second by meter square is the unit of viscosity. Pascals is Newton by meter square. So second, Newton second by meter square is unit of primary viscosity, and specific heat at constant pressure is 1 kilojoule per kg K. Thermal conductivity is something. The the same problem we have discussed with the previous one. We know that delta by delta P to the 1 by 3. So this equation is U Cp. So mu is 0.001 and this is 1000. He has given Cp 1000 and that divided by 1. So 1 kilojoule means once again this is 1000 joules. So this is 1000 and 1 is the thermal conductivity is 1 here. So this is 1. So delta is equal to 10. This one. So for air near atmospheric conditions flowing on a flat plate, the laminar thermal boundary layer is thicker than hydrodynamic boundary layer. This is false. So when our plate is submerged at an angle, with the direction of flow of liquid, it is subject to some pressure. What is the component of this pressure? In the direction of the flow of liquid known as, it is opposite drag. Anything you consider, when the flow fluid or air, whatever it is, when it is flowing over some structure or whatever it is, then if you resolve the resultant force in the direction of motion, that is obviously the drag. So the drag force exerted by fluid on a body immersed in the fluid is due to. If you consider here, we have a pressure drag and friction drag while deriving the equation. So pressure drag and friction drag. So the answer is pressure and viscous forces. So viscous is due to friction here. So answer is A. So the drag force exerted by fluid on a body immersed in the fluid is due to. So this is a repetition, but it is same pressure force and viscous force. So whenever a plate is submerged at an angle with the direction of flow of liquid, it is subject to some pressure. What is the component of the pressure in the direction? So the same repetition. So here CSA is repeating the same question. So this is drag here. An automobile moving at a velocity of 40 km per hour is experiencing a wind resistance of 2 kN. The automobile is moving at a velocity of 50 km per hour. The power required to overcome the wind resistance is. The power P is equal to FD into V. As you know, FD is CDA rho v square by 2. So the power is drag force into V, or in other words, you can say that power is proportional to. So here we have V square here and here V here. So we can say. So this is a drag force. As you know, we have given CDA rho v square by 2, and power is drag force into velocity. So this is. So FD CDA rho square by 2. So which is equal to 8 V. Or we can straight away take the power is proportional to V cube, because we have V square and V here, and P2 by P1 is equal to V2 by V1 whole cube, and P2 we have FD1 V1. This is P1. P1 is FD1 V1 into V2 by V1 whole cube. So this is you know here. So this value is 2 and 40 kilometers per hour. So he has converted 40 into 5 by 80 meters per second and 50 by 40. So this is 50 and this is 40. So finally it is 43.4 kilowatts. So which one of the following causes lift on an immersed body in a fluid stream? The answer is D. Dynamic fluid force component exerted on the body perpendicular to the approach velocity. Lift, always you consider the force in the perpendicular direction. Perpendicular to the normal, perpendicular to the direction of the motion of anything. So the fluid force component exerted on the body perpendicular is lift force. So he has asked about lift. Which one of the following is correct in the past buffing body? The answer is C here. The pressure drag occupies the major part of total drag. The pressure drag occupies the major part of total drag. So the answer is C here for the statements of the statement. Pressure drag cannot be smaller than pressure drag. Always the pressure drag is the major part of total drag. Improved steaming produces a 25% reduction in the drag coefficient of torpedo when it is traveling fully submerged, and assuming the driving power to remain the same, the increase in speed will be. So it has an equation here, CD1 V1 cube is equal to CD2 V2 cube. Remember the relation. So V2 by V1 is equal to cube root by CD1 by CD2, and it has given 25% reduction, means the earlier is 100 and now it is 75. So 100 by 75 and cube root it is 1.10. So the answer is A. So that means 10% increase here. Answer is A. So match the list here and list 2 and select the correct answer. So the answer is C here. So the Stokes law is 2, and similarly the streamlined body, see the streamlined body, this is skin friction drag. So the matching is C answer 2, 3, 4, 1. Again match list here. So the answer is C. Formation of cyclones. So C. Vortex flow. Simple matching here. The answer is C. For A it is 3 and B It is 4, turbulence. Velocity profile in a pipe is initially parabolic and then flat as this turbulence here. The answer is C here. So one more question. Streamlines inside a bond layer over a flat plate. What happens here? So this is a growth of bond layer as we have discussed here. This is a laminar bond layer and turbulent bond layer. It is a transition laminar sublayer here. It is a transition zone, laminar zone, transition zone and turbulent zone, etc. So here obviously the streamlines, because this is diverging, you can also say that it is diverging. So the answer is B. This is a simple problem I has given for one mark. If delta 1 is the thickness of laminar boundary layer at a distance of x1, so he has given delta 1 at a distance of x1 from the leading edge, the thickness delta 2 at a distance of x2, delta 2 at a distance of x2. Simple equation, as you know, the thickness of the boundary layer or the laminar boundary layer, that depends on, so this is the laminar boundary layer zone, this is only for laminar boundary layer zone. So this distance is definitely the laminar boundary layer zone, so that's why delta is proportional to square root of x, delta 1 by delta 2 is the square root of x by x2. So he has given the relation x2 is 2x1, x2 is 2x1, so I can substitute the value of x2 is 2x1, so this is equal to 1 by root 2. In other words, delta 2 is equal to root 2 of 8,1, so the answer is D. Simple problem, only understanding here. So the flow separation is likely to occur when the pressure gradient is, when the pressure gradient is obviously positive, the answer is positive. So the answer is positive here. We have the explanation, but when the pressure gradient is more than, when the pressure gradient is positive only, then you can expect separation of the flow, which we have discussed at length. An immersive body in a flowing fluid, lift force is, again, if you see here, the dynamic fluid force component normal to approach velocity. The answer is D here. So we have discussed here at length while you are discussing. So the answer is D here. So lift force always normal to the direction of the motion of the fluid here. The boundary layer in a thin fluid region close to the surface of the body where viscous forces cannot be neglected. So the answer is D here. You cannot neglect the viscous force. The definition of the boundary layer is the velocity change from 0 to free stream velocity, 0 to 99% of V, free stream velocity. So here this is all because of viscosity here. So viscous forces cannot be neglected particularly for happening of boundary layer. And velocity changes will occur only if viscous shear force are considerable. Velocity distribution in the boundary layer flow over a plate is given by, so he has given U by UM is equal to 1.5 mu, where mu is y by delta. Y is the distance measured normal to the plate and delta is the bounded thickness and UM is the maximum velocity at y is equal to delta. If the shear stress tau acting on the plate is given by tau is equal to K into mu UM by delta, where mu is the dynamic viscosity of the fluid and K takes the value of. It is asked to find out the value of K. Simple problem. So tau is equal to mu into d by dy, Newton's law of viscosity, and he has given U by UM is 1.5 N, and which is equal to y by delta he has given. So U is equal to 1.5 y by delta and UM, and UM is maximum velocity, and you can find out d by dy. So d by dy is y is 1 here, so it is equal to 1.5 EM by delta. So this is 1 if you take d by dy. So same equation, and tau is equal to mu into 1.5 EM by delta, 1.5 EM by delta, which is also equal to K into EM by delta. If you compare these two, and K should be equal to 1.5. So another equation here, a flat plate is kept in an infinite fluid medium. The fluid has a uniform free stream velocity parallel to the plate. For the laminar boundary layer formed on the plate, pick the correct option matching. So the boundary layer thickness increases in the flow direction. So answer A, 2. And shear stress on the plate, decrease in the flow direction, and pressure gradient along the plate is on same. So this is the answer is D here for 9. You have the explanation here, ABC, what exactly happens. And then 2 marks question. An aircraft is flying in level flight at a speed of 200 kilometers per hour through an air of which density is 1.2 kg per meter cube and viscosity mu is equal to 1.6 into 10 power 5 kg meter by second, and the lift coefficient at the speed is 0.4 and the drag coefficient is 0.0065. The mass of the aircraft is 800. The effective lift area of the aircraft has asked you to find out. So take a small problem on that. Very simple one. Speed of the aircraft is equal to 200 kilometers per hour, and you can convert into 5 by 18 meters per second. 200 into 5 by 18, 55.55 meters per second, and density of air has given 1.2 kg per meter cube, and mu is the viscosity of the air. It has given 1.6 into 10 power minus 5 kg by meter second, and CL is the quotient of lift and CD is the quotient of drag 0.0065. And what is mass of the aircraft, which is equal to 800 kg. Then he has asked to find out effective lift area of the aircraft. Effective lift area of the aircraft. Under dynamic equilibrium, you can take that. So this weight force, you can take m into z, and lift force is CL rho a square by 2, as you know. The general expression is always required for the problem. So drag force is equal to CDA rho a square by 2, and lift force is equal to CLA rho a square by 2. This is always required for you to remember to solve the problem. So here this is M100, I mean mass he has given 800, mass 800 into 9.81, which is equal to CL is 0.4, and rho he has given 1.2, and area is not known, and velocity in meters per second 50.55 square by 2. So simplifying A is equal to 10.6 meters square. This is another problem. It has given the data thin plate of 0.5 by 0.7 meters in size settles in a large tank of water with a terminal velocity of 0.12 meters per second. The coefficient of drag is 0.12, and also it has given the expression CD is equal to 1.328 by square root RL for a laminar boundary layer, and CD is equal to 0.072 RL to the power of 1 by 5 for a turbulent boundary layer. It has given the expression also, and where RL is the plate Reynolds number, and assume mu is equal to 1 into 10 power minus 3 Newton second by meter square, and rho is 1000 kg per meter cube. The subordinate of the plate he has asked here. So the plate dimension has given, so width is 0.5 meter, simple problem. Width is 0.5 meter and length is 0.7 meters here. Terminal velocity has given 0.12 meters per second, and he has given quotient of drag for laminar boundary layer, drag for turbulent boundary layer. Dynamic viscosity of the water has given 1 into 10 power minus 3, and density of water is given 1000. To know the type of boundary layer growth, you need to use Reynolds number here. Whether you want to use CD for laminar boundary layer and turbulent boundary, as it is different, first you should know whether the flow is laminar or turbulent, then you can use the appropriate equation here. So Reynolds number is 5 into 10 power 5. I told you during the discussion, when the Reynolds number is less than 5 into 10 power 4, this is only for a boundary layer, whereas for the pipes it is less than 2000. So when the Reynolds number is less than 2000, then it is the flow through pipes. When we consider the boundary layers laminar, a flat plate, etc., the Reynolds number is 5 into 10 power 5. So then find out the Reynolds number here. It has given rho 1000 and velocity 0.12 and length 0.7 and mu value. So from that find out Reynolds number is 0.84 into 10 power 5, As it is less than 5 to 10 power 5, so this is a laminar bound layer. So you can use a laminar bound layer because the Reynolds number is less than 5 to 10 power 5. So CD is equal to 1.328 by square root RL. So 1.328 by square root 0.84 into 10 power 5, which is equal to 0.0046. So one side drag force FD is equal to CD into rho AB square by 2. So CD is 0.0046 and the rho is 1000 and the area is 0.5 to 0.7. So area is 0.5 to 0.7 and the velocity is 0.12. So you can use all these values here and this is 0.00159 here. Drag force, this is only for one side. If you consider for both sides, it is 2 into FD and which is equal to 0.0231. 2 into FD is 0.0231 newtons here. Another problem, the thickness of laminar bound layer on a flat plate at a point A is 2 centimeters and at a point B 1 meters downstream of A is 3 centimeters. What is the distance of A from the leading edge? Very simple question, it is interesting. It is A from the leading edge. A from the leading edge. Very interesting question here. So here, if you see here, the laminar bound layer, the thickness proportional to square root of x here. He has given 2 points here, A and B. A and B. Delta 1 is 2 centimeters and delta 2 is 3. And the bound layer thickness here is 2 centimeters and bound layer thickness here is 3 centimeters. So we have the equation delta is proportional to square root x and delta A by delta B is square root of xa by xb. And the A point location is x here and B point location is x plus 1. So that's why xa is A, xb is x plus 1. So x by x plus 1 and delta A by delta B has given 2 by 3. This is 2 and this is 3. Simple example, simple mathematics we can find out the value of x here. 2 by 3 is equal to square root of x by x plus 1. So find out x here which is 0.8 meters. The only thing is required to know this delta is proportional to square root x. That is the only thing. An automobile with projected area 2.6 meters square is running on a road with a speed of 120 kmph. The mass density and the kinetic cost of the air are 1.2 kg per meter cube and 1.5 into 10 power minus 5 meter square per second. Respectively, the drag quotient is 0.3. He has also to find out two questions here. Drag force on the automobile is. Simple equation, and he has given the projected area 2.6 meters square. So the velocity v is 120 kbs. So 120 into 5 by 18 is 33.33. So convert kilometers per hour into meters per second. And rho is 1.2 kg per meter cube, and v is equal to 1.5 into 10 power minus 5 meters square per second. So the drag quotient has given 0.3. So you can substitute all these things here. Fd is equal to cd into a rho a b square by 2. So cd is 0.3 and rho is 1.2 and area is 2.6 and the velocity 33.33 square by 2. So this is equal to 520 newtons. Again, for the same problem he has mentioned, he has also to find out the metric horsepower required to overcome the drag force for the same problem. So the metric horsepower required is Fd into V. So we have the value of Fd is 5 newtons, 520 newtons here, and the drag quotient is 0.3. So you can use these values here, and velocity is velocity is 33.33 here, velocity 33.33 and Fd value 520. So you can use these values here, Fd into V. So 520 into 33.33, 332 watts here. And this is a standard 1 MHP is equal to 735 C. Answer is C. So thank you very much. I have completed the bond layer chapter. Interesting, we will take some 10 minutes time for interesting objective questions in general, which covers almost all the chapters, a short while for about 10 minutes. Simple questions and logic questions. I will quickly go through in 10 minutes and will complete in time. So which of the following forces does not act on a fluid? Which is torsion. Suppose if you see here, all the other forces are acting on fluid. Torsion is entirely different. Torsion does not act on fluids, all other forces act. A typical question. But the lift and drag and the boundary layer is slightly different orientation type of chapter. You need to concentrate and try to understand the question and answers, and that part also can be compared to other parts. It is slightly difficult, but you can easily able to get the answers provided you know the theoretical background and the discussions what you had so far, and you can get the answers. So the friction factor is a typical question. So it's all friction factor is FL square 2GD. But not only this also depends on all these. But in addition to that, it majorly depends on age of the pipe. If the more age, there will be a roughness on the inner wall of the pipe. That is a major factor in addition to other factors here. So age of the pipe is the appropriate answer. Slightly typical here. Pick the odd one here. So if you see all the instruments, Venturi meter, nozzle meter, rotometer, orifice meter and bend meter, etc. All these are measuring discharges except rotometer. Rotometer is for, it gives the discharge directly. And all the other will be using a differential manometer for measuring discharge, whereas this rotometer, it gives a discharge directly. Another one, we have all the equipment here. Petard tube, current meter, rod float, hot wire anemometer. These are all for measuring velocity. ABCD for measuring velocity, whereas the rotometer is for finding out discharge. This is a different type of asking questions here. The velocity flow at the outlet of the siphon of length 1 is given by. At the outlet of the pipe, as you know, we have losses here. If you, this is the exit loss, entrance loss here, head loss at the entrance. So H is, as you know, total head difference. So this is the entrance loss, 0.5 V square by 2G, and this is the friction loss, 4 FL V square 2G, and this is the exit loss. We have 3 losses here, 0.5 V square by 2G, 4 FL V square 2GD, and V square by 2Z. So V square by 2G plus 0.5. So 0.5 4 FL by D plus you can take out V square by 2Z. And if you simplify this, V square is equal to 2GH by 1.5 4 FL D. This one. This is very simple, provided you know all the 3 and you can straight away give the answer here, 5B. In equivalent pipes, dash and dash are same. Definitely discharge and head loss. We have made head loss equal to all the other losses and also discharge. And suppose if you see here, pipes in series, HF is equal to HF1 plus HF2 plus HF3, and Q is equal to Q1 is equal to Q2 plus Q3. So pipes in series, the head loss for the friction pipe is equal to sum of the head losses here, and the Q, same quantity is flowing through all the pipes. For pipes in parallel, HF is equal to HF1 is equal to HF2 is equal to HF3, and the Q is equal to sum of the discharges here. These two are the differences between the equations. So if friction factor is 0.04, this H is constant is taken as. So you can take straight away this equation. I have discussed this while you are doing some gate problems. in the discussion also. So I can scientifically take C is the square root of 8G by F. So 8 into G is 9.81 and F is, has given 0.04. You can scientifically take, find out C here. Instead of remembering all this, you can scientifically take and C is 45. This is also interesting here. The people are confusing this hydraulic radius of a pipe of diameter D and running not full, running half full. So running half full, running full means that is different. Running full means it is also D by 4. R is D by 4. When it is running half full, what exactly the hydraulic radius here? No doubt it is wetted area, wetted perimeter, wetted area. Instead of pi d square by 4, you need to use pi d square by 8, running half full. So pi d square by 4 is full, running full. Running half full means again by 2. So that is pi d square by 8. Again wetted perimeter, not half, as it is half here, pi d by 2. So this is also equal d by 4. So whether it is half full or running full, the hydraulic main radius is d by 4. Interesting objective question. You can expect in GATE such type of examinations. The other problem, hydraulic radius of a channel of a square cross section of side A. So this is a channel. This is a channel. Channel is not full. It is open channel type. Square cross section. The cross section is square, running full. But no doubt the area, the cross section area is A square. And if you see here, the perimeter is not 4A, it is 3A. The interesting here is because the top is open. Channel means, so he deliberately gives channel. If it is a pipe, that is different, 4A. If it is a channel, you need to take 3A. So the answer is A by 3. So it is normally, it will be confusing for some of the students because it is an open channel, you can take 3A. The answer is A by 3. The other one, the hydraulic radius of the pipe running full to the hydraulic radius of channel of square cross section. Just the ratios difference. Diameter is 5 here, the side of scale is also 5. The hydraulic radius of the pipes is the area of flow by wetted perimeter. The area of flow is pi 5 square by 4 by pi 5. The normal procedure pi by 4. The channel, once again the channel is different here. The area is 5 square, the side is 5 square. And wetted perimeter is 3, 5 because it is channel, not 4 here. If it is a 4, then that is a different aspect. So this is 5 by 3 and hydraulic radius of the pipes by hydraulic radius of the channel 5 by 4 by 5 by 3 is 3 by 4. If it is both 5 by 4, 5 by 4, the answer will be 1. Not like that, this is a typical question, 3 by 4. Cavitation is associated with, again it is low pressure. Again it is low pressure. To avoid cavitation, the venturimeter connected to pipe of diameter D. Cavitation obviously low pressure, angle of divergence is less than 7 degrees, so the answer is A here. The compound pipe consisting of several pipes of varying diameters and lengths may be replaced by an equivalent pipe. So this all you know, L by D5 is equal to L1 by D15 plus L2 by D25 plus L3 by D35. You can cite away, remember the equation, you can get answer 16C. So the other problem, so the specific gravity has given 0.75 and suddenly expands from 0.5 meter to 1 meter, head loss due to sudden expansion. So it has given discharge. So you can find out velocity here. He has given discharge, the area pi d1 square by 4 and pi d2 square by 4. So you can find out the velocity v1 and v2, and the equation here is v1 minus v2 square by 2z, velocity 1 and velocity 2, and you can get the head loss due to sudden expansion, v1 minus v2 whole square by 2z, which is 11.95 meters. So the static and the stagnation pressure of a petard tube of a quotient 0.9 or 5.5 meters and 7.5 meters, velocity of the stream. So which is equal to V, but actually we require a dynamic head. Dynamic head is the difference between static means total and stagnation pressure. So this is static has given 5.5 and stagnation is total. So 7.5 minus 5.5 square root of 2z, and this is 5.63 meters per second. Okay, so these are some of the interesting questions, and thank you very much for listening me from the last 12 days. I'm extremely happy that some of the students are really they have asked me very interesting and good questions, and I try to answer them in a perfect way. And definitely, a fluid mechanics subject is interesting subject, but as you know, it requires the knowledge of mathematics, and also we require slightly physics and the concepts of engineering mechanics, center of gravity, moment of inertia, etc. And if you have the fundamentals, the complete theory and the relevant equations, and also we had solved some of the problems of gate also, the theory and solutions, and be confident and be sure that they will be getting good marks in gate examination in the subject of fluid mechanics. Almost I tried at my best to give a complete information of fluid mechanics, covering all the chapters right from the beginning: fluid properties, hydrostatic forces, and pressure chapter, and fluid kinematics, and fluid dynamics, the chapters, and again analysis of flow and applications of Bernoulli's equation, and also the notches and orifice, and also drag and lift and boundary layer. All the chapters are very, very important, and try to see that you are comfortable and should be confident enough to write the correct answer. Maybe slightly try to, the gate examination paper will be set such a way that it slightly confuses you in a bit for answering the questions, but try to be confident and try to give right answer for the question, and try to understand the question properly, and within no time try to give appropriate answer. So because out of all the 4 A, B, C, D, and 2 answers might be close and might be correct. Again, I thank the organizers, particularly the Satyanarayana Garu, and also civil side, Reddy Garu and Madam Geeta, and not only them, and initiation by the Vice Chancellor of J.12 Anantapur, Professor Srinivas Kumar Garu, was colleague for me from the last so many years here when he was here, the Vice Chancellor of J.12 Kakinada, also a friend and colleague to me, Professor Ramalinga Raju Garu, and their active initiation also G.V.R University authorities. When I was a registrar almost for a period of 4 years, I have a good contact with all the universities. I am happy that they have taken such an innovative and good idea under the leadership of the Honorable Minister Suresh Garu, and also Principal Secretary, Special Chief Secretary Higher Education Satish Chandra Garu, and also the dynamic personality Chairman State Council of Education Professor Hamchandra Reddy Garu. Even though he was busy and very busy, but he has taken classes for mechanical students. I think mechanical students are also here, and such a wonderful personality. In addition to his administrative work, he has taken the classes, gate classes for you, the government mission he has fulfilled, and also as a Vice Chancellor of the J.12 Anantapur, he has also taken classes for ECE, and they are also motivating force for me as a rector. I have taken classes for you from the last 12 classes, and here and there, if I miss anything, kindly forgive me from the organizer side and also from the student side. But I am happy with you and happy with the students. And also, I also thank acknowledgements to the references, fluid mechanics and ideal machines, Modi and Sheikh Bansal and Monda. Fluid mechanics has given a lot of information on that, and also gate questions from ACE. In addition to all these things, and my friends who have helped me to a great extent and supported me and encouraged me in all aspects, the faculty member of my own colleague, and friend. In addition to that, and my own students, a research scholar, and the student friend of PG now, and also my personal secretary, and they have helped me to give a better information to the